How you doing? It feels like fall. It's wonderful. My name is Aaron Mazzeo, and I am in the Department of Mechanical and Aerospace Engineering. And this is going to be our semester covering mechanics and materials. I hope that you'll enjoy the course. It's kind of a work in progress. We're iterating, trying new things, and in some cases going back to old things. So as we go through the course, please feel free to provide respectful feedback, and I look forward to getting to know many of you better. We have a pretty full class at this point. If anyone is in here and has had trouble getting onto Canvas, just stay after for a few minutes. We'll get you on even before the registrar is able to get that. Assuming, of course, the registrar approves that you'll be in the class, then you'll be all set as the semester goes on. Today, it's going to be a little bit of your typical introduction, and then we'll get into some of the aspects of units, which you are already probably accustomed to seeing, and then we'll get into scaling relationships for some mechanical systems. Okay, so here are some data or some basic information. We have a wonderful teaching assistant. Oh, there he is, Praj. Do you want to introduce yourself?
Hello guys. First year PhD student. I'm working with Professor Fazil's lab and I'm doing this like for 3 consecutive semesters. So if you have any doubts, please feel free to contact me.
Right. So Praj and I, we did some new things together the first time. Then he had an opportunity to do some other things with a different professor last semester, and now we're back together for this. So he will be a wealth of information. His contact information is up there. I don't know, do you have a preference for Canvas inbox or for your email? Email, okay, so if you'd like to contact Praj, please do so over email. I have a preference for Canvas inbox. Of course, you feel free to send me an email about things relative to engineering, generally speaking, the department. I am serving as the aerospace undergraduate director, so if you have questions along those lines, that's great. Email or whatever you like. If it's something related to the course, for your own sake and for my sake, and so it doesn't get lost, use Canvas inbox. Okay, that's my preference. We also have a GroupMe, and many of you have signed up for that, so thank you. That is a place where we can respectfully work on problems together or solve issues that may arise. So there's a link in the syllabus that you can access or in the announcements that were sent out yesterday. We have Canvas, and we have a couple of other websites. So much of the content that I hope you'll find useful is on this other website, engineering-content.com, and we have a course here. And in fact, I just uploaded the PDFs for today. So if you want to download those PDFs, you're welcome to do so. You'll also find past exams. Probably we have about 5 or 6 years of exams now. Okay. And so that will be a resource for us as we go forward. And then there's not of course, but there is YouTube as well. Both the stuff that you'll see from this room, stuff that you might see from past semesters, and then welcome you all to watch some Jeff Hansen or watch some of the other people out there. And you'll see on the website that we have some of their embedded YouTube videos there for your joyful viewing. We will do a little bit of finite element analysis, which is just a fancy way of saying we're going to do some simulations. There will be 3 of those homework assignments, one that covers bars, one that covers twisting of shafts, and another that will cover beams. So you don't need to download any proprietary software. We're going to use kind of open source solutions to do these homeworks, and then when you take multi-physics simulations, which you might get an opportunity to have me again, for better or worse, we'll use ANSYS. Okay, that's one of the commercial standards out there right now. And then there's an opportunity to use Python. All right, and I know many of you are familiar with, hopefully most of you are all familiar with MATLAB. Python is very, very similar, and it's open source, and it's something you probably want to know for your careers going forward. This is by no means an extensive course on Python. It really is putting in scripts that are similar to a calculator, right? I know you all love Desmos. Well, okay, maybe you don't love Desmos, but a lot of you like Desmos. Please feel free to use that as well. There are a couple examples where I do think that if you just use the scripts that we provide, it will save you tens of minutes, if not an hour, okay? So sometimes it's just easier to use what we give there. And the Python code is going to be available also on this website that you see here, okay? Okay, textbook. There is not a required textbook, but if you want a textbook and you like a textbook and you learn very well, and quite frankly, you can learn things that we won't cover here in this class together, and when we're meeting together, get Hibbler's textbook, all right? It's that simple. And the first, you might get frustrated because you're like, well, this is not following the first few times that we meet, because I have kind of some things I like to cover with the units, some scaling, what we're going to cover today, some stuff on thinking of systems as springs or mechanical systems as springs. So you're like, why do I have to? Once we get to the third meeting, okay, that's when we start to really follow Hibbler quite well. Okay, you'll see extensive reference to Hibbler's text and stuff in the slides. So, I had one person once at the end of the semester say, "You never told us we could use a textbook." I'm like, the textbook, I said you could, I listed Hibbler, right, on the syllabus. But, I understand it's not required, so you may not want to get it. Do I think that we cover enough in the class to cover the exam problems and everything that you're going to be responsible for? Yes. Do some people learn by reading? Of course, right? So again, just if you want a textbook, get Hibbler's textbook, but don't pay for Mastering Engineering, okay? Because we're not going to use that. We're going to use Canvas, right? And now, yes, a lot of these problems are out there. That's fine, whatever. I guarantee you that the exam problems will be at least somewhat original, right? I mean, you can look at the past 5 years of exam problems, okay? So do the homeworks, right? And they should be on the easier side, especially, I hope this semester I'll have a little bit more time to provide some additional content so that you actually get some examples of how you do the problems, okay? If you took this, or if you know people who took it last fall, we did a flipped classroom thing. The students, you all, your peers, they told me they did not like it, and very, very, very bluntly in some cases. So we're going to do more of a traditional format here, okay? Here's the schedule. So it's pretty intense, all right? We have, when you look at it this way, it's like, how are you going to get through this? Okay, so it's just a bunch of text. But there are 3 exams. Those dates are set. I'm going to try very hard to get 1 or 2 additional rooms for the exams, because this is not, look around, right? I may end up eating my words. If there's nothing available, right, there's nothing available. But we're going to try to have people split up into multiple rooms. Okay. Let's see, okay, and then the final exam is already out there. That one will be, I guess, 8 to 11. And we'll also probably try to figure out how to have a split up. Okay. We will have labs as well. Well, 1 lab that everyone gets to do. Okay. So the way that's going to work, in a few days there will be a sign up. Okay. And that lab session is actually going to run, because for the sake of scheduling, it's going to run at the same time as this class. Okay, so we're going to have a lab assistant over there, and she's going to be great. She's taken class before, very, 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 very bright person. So she'll be helping you in the lab during that session. Of course, we'll have some material for you to review beforehand to make it go a little more smoothly. but it'll just be one lab where you work in teams of 3 or 2 or 3, okay, and there will be 3 concurrent teams. We have 3 testing machines in that lab, so there will be 9 people in the lab. And that's going to be just around, where are we? It's going to be in the D wing, all right? And the room number D123K is there. Okay. In terms of the breakdown of the grading, I've played around with the percentages. I think this semester this will work nicely. You notice the homework and the attendance and the lab are worth 30% of your grade. Okay, so if you show up and you do the homeworks, you've got a good chunk of your grade done. Okay, so the averages of the class are better, or also look nicer to me when you do it this way, right? Of course, the exam grades typically are going to have, they're going to be hard. Okay? They're going to be hard, but they're going to be manageable as we go through this together. There is so outside of that 100%, there is this 1% bump. So if you participate in class, if I get to know you a little bit, and you're within 1% of the thresholds, whatever they might be, you get a bump. All right. Any questions up to this point on what we've covered? Yes.
Can you go a little bit further into the labs? Like, how exactly is that going to work?
Okay. So what's going to happen is you're going to sign up on a spreadsheet, a Google sheet. Okay, and if you want to sign up with 3 other buddies or not, whatever, it's just going to be first come, first serve. Okay, so we're going to have you're not ready to do the lab yet, but after like the 3rd or 4th time we meet, you'll be ready to do the lab. Okay, and it's a nice little setup where we essentially pull materials apart and we characterize things like their elasticity, their toughness, their resilience. And then there's like a little design aspect where you get to kind of build a test structure and predict at what force it's going to fail. So that is going to happen in teams of 3, and it will happen at the same time, like I said before, as you meet here. So if you miss, this is a point, if you sign up for that one session, okay, that you're going to miss here, and obviously it won't be on an exam day. Okay, we're not going to do that. That would be silly, right? You're still responsible for the homework, okay? But you'll be able to watch, the recording of whatever you miss. Okay, does that make sense? Other questions? Yes, over here.
Are all lectures worth?
Yes. Yes.
Would you say we should get the textbook or is it fine?
I'm gonna say, if you're gonna get mad at me because you didn't have a textbook, you should get the textbook. Okay? How does that sound? Okay? You all, right? And I guess on the aspect of the textbook, you don't have to get the most recent version. Okay? The ideas, the concepts, the theory that are presented in this course have not changed for some time. Okay? And Hitler's books are great, and they have various reasons for, I think, coming up with editions every few years. But just get an edition, probably from the last century, and you'll be okay. Okay. If you might get a little upset because I was trying to kind of align to try to point out some of the sections in the textbook, how it maps. I don't have a complete mapping, but goodness, that book has all these pretty pictures in it. You just flip to the right chapter and look. You'll be able to see a lot of parallels between what we're doing in class and what's in the book. Okay. So other questions? All right. C, I think we might be ready to go. Okay, so what I want you to do is start going, right, attendance. Okay, I didn't talk about that. Okay, so the way attendance is going to work, okay, is, and we can go ahead and do that now, we'll just get it out of the way, because a lot of you are here, all right? So the way this is going to work is you're just going to take a selfie with the screen, and you're going to upload it to Canvas, all right? And you'll be surprised. You can take a selfie. Okay, so go ahead and get your phones out right now. Okay, you can take a selfie, all right, without getting anybody else, including me, in the screen and your face, okay? And then what you're going to do is you're going to go up to Canvas and you're going to upload it right now. It should be available. If it's not, take the picture and you can upload it later, right? But I'm pretty sure I got it right. Okay, so go ahead, take the picture of yourself and the screen. And make sure your face is in it, okay? All right, and so you should see, you should see on Canvas that you can upload, you can certify that you're here, and then you can upload it, okay? Okay, that works too, yes. We have that's awesome. That is awesome. All right. Okay. So that's how you get your 5%. Of course, if you have an excused absence, all right, please contact the Dean of Students or fill out the SSRA form, okay, and they'll send a note and send me a note as well, okay? Excused absences in this class will just count as you were here, all right? I don't know if anyone cares, right? So there are 25 meetings that we're supposed to have, okay? So if you have an excused absence, it won't become like you got 24 out of 24, you'll get 25 out of 25 if you made all of them. When you're in the lab, that one day you're in the lab, just take a picture and hug the machine, okay? And upload that one, all right? You don't hug the machine, all right? But you know what I mean, like just whatever, take a picture with the machine. All right, any questions?
I'm sorry, where are we uploading?
So in Canvas, all right, there should be an assignment called Attendance 9-3, all right? And then that's where you will upload it, okay? And there'll be Attendance 9-4, and you have up to 10 minutes after class, all right? All right, so now we're also going to use Canvas again to do the first 3 problems, which count for 0 points, okay? So what I would like you to do, okay, and we're going to talk about this a little bit. We're going to talk about, okay, some of the materials that shape your lives, all right? We're going to ask you, why do you think that these materials break, okay? And then I'd love to hear what you have to say about what you hope to learn this semester in this course. Okay? So take a few minutes, and I'll log into Canvas to try to look at your site, look at your responses. But you can also verbally shout them out in a few minutes. Okay? So these questions, all right, this is how they should appear in Canvas. All right, so here they are again. Okay, what are 2 materials? Okay, and this is just to get you familiar. Yeah, I guess I should have said that point earlier. This class goes pretty fast in that you have problems that are due at the beginning of the next class. The awesome thing about this semester is that we meet on Tuesdays and Fridays. So you've got 2 days in between today, whatever. We know the days of the week, right? Yeah, I think I know the days of the week, right? So you've got until the beginning of the next class to answer the questions, okay? And it'll just keep going like that, all right? So these are worth 0 points. So don't ask me afterward at the end of the semester, I didn't get credit for the first 3 questions. I was like, yeah, they were worth 0 points, okay? But this is just to get us warmed up. Okay, someone said paper. Yes, paper is one of my favorite materials. Okay, in our lab, we will look at making devices, robots, electronics out of paper. So I like paper. Okay. I like the other materials too. Anyone have an idea which material we're going to spend the most time talking about in this class? Who said steel? Yeah, that's pretty much our material of choice this semester, okay? We'll also talk about other metallic alloys, aluminum for example, but steel is going to be our biggie. Okay, what else are people saying? Wood? Okay, I like wood too. In fact, paper comes from wood. Okay, good. Graphite. Why did someone say graphite? Why did someone, of all the materials, why graphite? I don't know who you are, but I guess I'll get to know you. But why graphite? Yes. It's a lot of different what? Yes, yes. It is. Like what kind of components? Can you be more specific? Yeah. It's in your locks, right? It's a good lubricant as well. Yeah. Has some interesting electrical properties. What's your name? Okay, you are the person. All right. Okay, what else? Okay, yes, plastic. What are your favorite plastics?
Nylon.
Nylon. Why nylon? Who said nylon?
Because I've 3D printed with nylon a couple times. I guess it just like feels really weird. Like I don't know, it's like a lot smoother and a lot more like I guess durable than other 3D printed materials.
Yeah, that depends on which ones, but if you're comparing it to PLA, polylactic acid, yeah, it's going to be a more durable material. Yeah, what's your name?
Joe.
Joe? Okay, good to meet you, Joe. Okay, what are some of your other favorite plastics? Polyester, yeah. Okay, why polyester? Clothes. All right, great. Yes, so it's another wonderful material that can actually crystallize either under stress or under heat. Okay, so I had an opportunity to work for a startup company, and we were making different types of sheets of plastics for spreading light or for diffusing light. And in this case, polyester was interesting, and it's more ubiquitous in packaging than I think most of us think. Of course, it's extremely common in clothing as well, but it can be made extremely thin by controlling its crystallinity through a mixture of heating and actual tensile loading, stressing, and biaxial stressing. Okay, polypropylene can also be controlled by biaxial stressing. Okay, does anyone play the game with their friends to identify the polymer? No? No, you don't. So like on a Friday night, you don't sit around and like be like, hey, that's a PET bottle. That's recyclable. Or that's polystyrene. That's my yogurt cup. No? Anyone? Okay, well some of you, I bet you some of you know the numbers better than I do. My kids know the numbers on the bottom better than I do at this point. Okay. But there are a number of interesting polymers. There are kind of two classes of polymers, too. Okay? There are those that you can heat and melt, and then cool, and then heat again. All right? And those are what we call thermoplastics. So that's, plastic, thermoplastic. Anyone know what the other class of polymers typically is called? Yes?
Resins.
Okay, resins are, yes, part of that class of... So thermo, not plastic, but thermosets. Who said that? All right, what's your name? Daniel. All right, Daniel. So what is a thermoset? Any ideas? Or did you in the purple back there, did you want to say what a resin is?
I mean, I'm only just familiar with resins since I work with fiberglass and surfboards.
For what, surfboards? Did you say surfboards?
Yes, that's what
Yes. Where do you surf?
on the beach.
Monmouth? Okay, yeah. All right, so I got some shoulder issues, but I love surfing. All right, so you got a surfer. You should come see me senior year. We do senior design projects on surfboard propulsion. Okay, good. But okay, so fiberglass. What is interesting about resin?
Is that you can kind of mold it, or you can use it to mold fibers onto any kind of shape to reinforce it and make it stronger.
Yeah. Okay. And it's one way, right? You can't, like, so if you're using epoxy or polyurethane, right? You can't melt it again to get it to become nice and soft, right? It's a thermoset, so it's cross-linked. Some examples of thermosets in your lives? Any ideas? So we said epoxy, polyurethane. Yes?
Is acrylic?
Okay, so acrylic. Okay, so there can be there can actually be like yes. So acrylates. So acrylic PMMA, polymethyl methacrylate. Okay, that one is typically a thermoplastic, so you can heat and cool it, right? But there are some acrylates, okay, that are often used for UV curable systems. Okay, so those, and when I say UV, I mean you shine light on it. It has a photo initiator which reacts with things that I don't understand, to be honest, but it then causes the polymer chains to bind and get links between them, and that's called cross-linking. Okay, good. All right, another favorite material of mine is silicone. Okay, and that's like you have silicone oil, which is just the polymer chains without being cross-linked. But if you put a cross-linking agent in there, or it's modified appropriately, then you get cross-linking, and that becomes rubbery materials. Becomes rubbery in nature. Okay, let's go on. So why do you think that the materials break? Well, let's see. You guys answered. I can look over here. Some of you answered. Okay. What do you all say? Why do materials break?
Weak bonds.
Okay, weak bonds. Go into that.
That materials stick together with strong forces.
Right, yeah, okay. Right. So, at a molecular level, right, we have these different covalent or bonds between interfaces of surfaces, or closer between the molecules themselves, of course. And we have to exceed some type of adhesive strength for these bonds to separate. That's why things break. Now, folks have written things like forces that are applied to the system and they cause them to break. Yes. Okay, so what we can do right now is distinguish between what is a structural property, okay, and what is a material property. So if you're thinking about forces and torques, and the applied force and the applied torque that you have to break something, do you think that's a structural or a material property? Material. Okay, it's related to material properties, which means I'm going to say it's a structural property, typically, okay? Because you go to some furniture store, right? And they're going to say, this is how much force this table can hold. Okay? They're not going to say, oh, we're breaking the molecular bonds of this material, and it's a pressure, okay, that's going to cause something to separate, or a stress or something. It's going to be a force or a torque or a moment or something like that. That's a structural property. Okay? So often when we say mechanical properties, we're not being very specific. Is it the structure that we're talking about breaking, or is it the material that we're talking about breaking? If the material is the thing we're interested in studying, then it's kind of this intrinsic property. Of course, it's related to processing, it's related to crystallinity, it's related to cross-linking, like we were talking about. It's related to a bunch of different things. Okay, composition, okay, heat treatment, whatever stress that's been induced in it. Even you can have hardening. Okay? We'll talk about a lot of these things actually in the class. that is kind of like though there's some pie in the sky, well maybe not pie, material in my hand, right, that doesn't have a specific form, right? And I'm going to say just like, you know, you've studied in other classes in physics, right, where you have, hey, there's a pressure, okay, there's a pressure. And when we talk about tanks, pressure tanks, which we will talk about as well, okay, that we do speak about pressure too, and that does relate to the structural and the material properties, okay? But typically, right, we're talking about, okay, you just give me a piece of material and it's gonna, you know, if I apply some type of pressure to it, I'm interested in understanding if it's going to break or not. Okay? So that's a material property. Structural property is more like you got a structure. What we do in this class, the classic point of this class, is not to take the Eiffel Tower and put it in a testing machine, okay? Or a bridge and put it in a testing machine. Although we do have a lot of testing at Rutgers that's related to bridges and safety, okay? So there are needs to do, you know, some testing of that nature. The idea though is someone says, I want to build structure, and they say it needs to be able to support this much weight. It needs to be able to support this much force. It needs to be able to support this much wind. It needs to be able to support this much shaking, vibration, whatever it is. And then we go to our database of materials and we say, okay, these are the materials that we have, and these are the material properties, and we have to assemble the material into enough mass, okay, to be able to get a structure that can support a load. Okay, so that's the difference between a structural property and a material property. And we're going to go back and forth because we're going to have different structures that we analyze, pretty much just three. We'll talk about this in a minute, but they're bars, shafts, and beams. That's what we study here. And you're like, those are really boring. Well, yeah, they might be, but they're pretty ubiquitous, actually. Okay, you just look around and say, oh, well, there are bars right there, you know, or wow, that kind of looks like a beam, although this is more of a plate in mechanics speak. The top of this table is what I'm speaking about. Okay, but there are analytical solutions to these. Once you get into more complicated structures, fortunately, we have been able to reduce our safety factors because we have good simulating capabilities now. Okay, and we have also a lot of experience, right? Don't underestimate the experience of other engineers who have built things in the past. Okay, they have some idea of what's going to happen. And so we're able to reduce the safety factors. Safety factors are just like the buffer, right? How bad do you think your calculations are, right? And so mechanical engineers, for better or worse, we operate, and safety factors are probably 2+. The aerospace engineers, because they want to reduce weight, they'll get down to safety factors like 1.17, all right? So just on the bleeding edge. And you're like, well, isn't that dangerous? Don't you want to have more safety when you have, you know, a rocket going to space? Well, do you want to take tons and tons of more material up there, which requires tons and tons of more propellant, or are you trying to find a happy balance? So aerospace structures have to be optimized for their mass. Anyway, we went off. The point is there's a difference between material structures, or there's a difference between the structural properties and material properties. Okay, so what do you want to learn about in this class? No one's wait, hold on. We have to refresh, I think. Wow, only 5 people answered this. Okay, well, that's what it says. I don't know if it's true. That can't be true. Okay. Right, okay, so we're going to cover testing. That came up? Yeah, no, more than that answered this. Okay. Polycarbonates. Okay. All right. That's interesting. I won't go into the material properties of polycarbonates if you're listening, but they are interesting materials. They have high impact strength, and they're nice and they're moldable. They have some issues in sunlight usually. So sometimes you'll be like, okay, is it polycarbonate or is it acrylic? And if it's going to be in sunlight, acrylic is naturally more resistant to UV light. But the stuff we learn about their strength and their elasticity, that will be relevant to polycarbonates. Okay. Yeah, right. We're going to attempt to get to understand where we should use which materials. Okay? They affect our daily lives, absolutely. Yeah, so we're gonna, this is, yeah, different materials and how one structure can be different from another. Okay, yeah, so we're already talking about the relationship between materials and structures. Okay, good, good. Any comments, anything you would like to add to this moment with these 3 questions? Yes?
When you say break, does that include like physically things breaking and also like corrosion and combustion?
Okay, very good question. What's your name?
Sure.
Sharice. Okay, Sharice. Okay, so typically in this class, we're going to say something fails when it goes beyond its elastic abilities. Okay, so a material like, well, a structure like this, when I sit on it, okay, when I get off, it should come right back up to where it was originally, as long as I stay below what's called a yield strength. Okay, so yielding is when we go from elasticity, we go over, and then it doesn't come all the way back. Okay, and that's, for most applications in engineering, that's not a good thing. Okay, because that means that now you've kind of accumulated some damage, and that can lead to a failure point. But it's pretty much unavoidable, especially at the micro scale. Okay, but when we say fail, we're interested in seeing, okay, did we go beyond this limit of its strength when it went from being elastic to being plastic? Okay, plastic is what we call this regime where you no longer go back. It's interesting because we just talked about plastics, right? But this in mechanics, it has kind of plasticity, has a special kind of meaning for what happens to a material. Okay, plasticity is actually kind of harder to model in many respects, okay? But elasticity is where we're going to want to reside. We'll cover both of these things. So when I've been saying break, I'm mostly thinking about when it starts to yield, which means when it starts to not be able to recover. But in DMC, design of mechanical components, you will cover corrosion, and if you've done some chemistry classes, we talk about corrosion and compatibility of materials. This is a problem. Why is it a problem? Because corrosion really means that the effective cross-sectional area, okay, so if you think I've got a bar, and now corrosion happens, and the cross-sectional area of the bar, I mean, corrosion by itself is not like really, really bad at 1 second, but, or unless it's like hydrofluoric. Anyway, but if you've got something that's really, really corrosive, right, like in the movies, or in the chemistry building, whatever, then you've got a problem. But the idea is that if I've got this bar and it corrodes, the effective cross-sectional area slowly decreases. And it decreases, and then what happens is the local levels of stress reach the threshold of the material, and that's why corrosion is a problem. Yeah, so we'll cover some. We won't cover too much of the aspects of effects of temperature, corrosion, those things, but we will focus more on the transition to yielding. Okay, so hopefully that helps, Sharice. Okay, so we've already kind of discussed some of this, and people have kind of written these things down. We do live in a material world, all right, and I'm made of material, okay? Some other singer would say something else. But we want to be able to understand when things are going to break, okay? And we get a bad rap as mechanical, and we'll include the civil engineers, because it's like something bad happens, and it's like it's so obvious. If you had just made it a little thicker there, it would have been fine. If you had just done, well, in some cases, if you had just followed some protocols and did some testing, you want to have things exploding underwater or imploding, okay? But you have to realize that it's kind of, in retrospect, it's very obvious to people what happened, and so for us, okay, we have to make sure that doesn't happen. when my computer stops working, I don't know what's going on. And it's like, ooh, the electrical engineers are so smart, right? Because you can't see what happened, right? Anyway, but we love being mechanical and aerospace and civil and any other engineer that has to deal with materials and why they break. Okay, so there's a good video here if you want like a better explanation than I can do of the general structures now that we're going to be studying in this class. But the first one is the bar, okay? Very, very simple. Okay? And you'll be happy when you see bars, usually, on exams and things, okay? This bar is floating in space. Why? Is it not accelerating, though, while it's floating in space?
Forces kind of each other.
Right, it's an equilibrium, right? Statics. Okay, so we want to make sure that our structures are either running at a constant velocity or not accelerating in this class. Or both, right? If it's at a constant velocity, then it's not, anyway, you know what I mean. At rest or not accelerating. Okay, the shaft. Why is this not accelerating? Because, yes, go ahead.
The sum of the torques is zero.
Right. Okay, and we're going to talk. You remember your nomenclature, right? You got the vector coming out of the face. All right. We're going to cover this at length, ad nauseum almost again. Okay, because that seems to confuse people. But would you say, if I'm looking at this, would you say that this is a positive torque on this end, externally speaking, or a negative torque? Yes, Joe.
Would that be positive if you're looking at it from the direction of that face?
Yeah. So if I put, if I've got the shaft here, right, and again this is 3, right, and I've got this torque coming out, or turning like this, right. This is the face. This is the arrow. That's a positive torque. Okay. Just like this is an open face and it's positive on that side, right. This is an open face, right. It's positive coming out. Okay. But with external equilibrium, well, we'll get into these balances. The internal equilibrium, yeah, we're going to say F minus F is equal to 0, right? Okay, but when we start taking slices and stuff, we're going to use more of this terminology, right, to see which one's positive, which one's negative. And this would be positive on this side, if I think of it that way, right, coming out that way, all right? But I'm going to say that, these are going to sum to be equal to 0. So when I do external equilibrium, I'm going off into stuff, I guess, a little bit. We'll get into this, don't worry, but since you got my mind going, right? When you do, remember you do 2 forms of equilibrium, right? You have the external equilibrium that you satisfy, and you have the internal equilibrium that you satisfy, okay? So when you do external equilibrium, and maybe my question was not well formed, right? This would be positive coming out of this side, but when I look at it on this side, it's going to be negative, all right? Because it's going the opposite direction relative to the positive vector coming out of that face. What I mean, the positive vector coming out of that face, right? Like here, okay? Okay, and then the last structure is the beam. So those are the 3. The beam often is going to be loaded transversally, okay? Or this is called transverse loading. What does that mean? Transverse means across, okay? So this is a bar. This is axial loading, but transverse loading of the beam means that we've got loads that are coming across, okay? Often forces, sometimes moments. And they are probably the most tricky to study. Okay. So here we go. These are the terms. Now, let's talk about units. When you walk around outside this classroom, what is your preferred unit of force? When you go out of this classroom, really? Pounds, right? We're in the U.S. So some of you, if you're from another country, yes, you're into kilograms, actually, which is not a force. And you probably don't even say newtons, right? But we don't say slugs. either, right? We say pounds, which is a force. Anyway, so it's all messed up, right? But yeah, so in class, right, we like to do newtons. You got to be able to convert between them. Anybody know how many newtons are in a pound? Huh? Okay, well, write it on your formula sheet, okay, for the first exam. It's about 4.5, I mean, I think it's right here. It is right here. It's about 4.5, okay, newtons in a pound. We will cover piconewton to meganewton. All right. What is pico? What's that prefix? Huh? Negative 12. Okay. And mega? 10 to the 6, right? Okay, good. Okay. We're going to have a lot of megas. We actually won't have many picos. All right. But we have a lot of megas, megapascals. We have a lot of kilonewtons. That's, of course, going to be 1,000 newtons. We even have kips, which are kilopounds. All right. So you should be somewhat familiar with these forces. So this is some interesting depiction of atomic force microscopy with a strand of DNA. And the idea is a bar in statics was just a bar. What do I mean by that? I mean it handled force. You didn't think, though, about how much it was stretching. Maybe, or did you? I don't think so, right? Not in statics. So if I put a load on it, right, it has some elasticity to it. Okay? It has some springiness to it. Okay? Just like this little thing of DNA, these strands of DNA. Okay? And so the elasticity of is, right, we talked about how you go into plasticity, right, when you exceed a certain threshold in yield strength. Okay? So DNA, in this case, is acting like a structure. Now it has some material properties to it, but it's in a coil, like a spring. Okay? And so for that structure with some wire diameter and some coil diameter, okay, which you'll talk about in design mechanical components, you'll do springs. You don't do them here, at least not the coil type. And so that will behave like an elastic spring at very low forces. So less than 10 to the minus 12 newtons. Okay? That's 10 piconewtons. Our dimensions go down to nanometers, to meters, right? So this is, we're down, DNA, that's nanometer level type of a material, or structure, probably better said. And nano is 10 to the minus 9, yes, good. Okay. So diameter of DNA is 3 nanometers, okay. The radius of a hydrogen atom, okay, is 1/10 of a nanometer, okay, or about an angstrom. And we're going to be studying these different types of materials. Okay, so this is the bar. Now, where do we use bars? We use them all over the place. Okay, posts or legs in compression, cables in tension, right? So those are like some famous examples that you did from physics. And also you looked at trusses in statics. Okay, now they can come in different dimensions with cross sections in this class relating probably millimeters to centimeters. Typically a bar is got a cross section. The dimensions of its cross section are going to be less than its overall length, right? That's typically how we think of bars. If you set something on a plate, you can still think of it as a bar, okay? But that's more of a plate than a bar, okay? And so the lengths are going to be longer, okay? So centimeters to meters. So if we go through, there can be different materials, different composites. If we look at this airplane over here, okay, a Boeing 787, okay, it weighs about 550,000 pounds, right? So it's like 275 tons. What is supporting its weight when it's on the ground? Well, that's something called a strut. All right. And do we have any car people here? Okay. I mean, I've never taken out a strut. Has anyone ever taken out a strut or their suspension? No. Okay, fewer and fewer, I guess. All right. I can't say I have either. I recently learned, though, that they make these little inflatable plastic things that you can insert in some of your suspension. So, like, if you have a trailer or a load that you're carrying and you want it to be more resistant, they make these like air bladders that you can put in. I thought that was pretty cool. Anyway, so a strut, okay, that is essentially a hollow bar. Okay, so a bar doesn't have to be solid either, right? And how many of those do you think there are? Well, in this plane, 3, okay? Or 3 strut systems, you could say, right? And my 7-year-old could tell me, he's like, yeah, they put like 8 wheels here, 8 wheels here, and 2 wheels up front. So that a lot of these jumbo jets have 18 wheels. I'm like, well, okay, I didn't know that, but that's interesting, all right? So there are a bunch of wheels, but then they go into these columns, these struts, all right? So if we're designing these struts, and we make this gross approximation that the load is distributed evenly on them. Okay, of course, we know that's probably not going to be the case, especially at the beginning of landing. Okay, when there's impact, which you'll also cover in design of mechanical components. Okay, and the back 2 struts are supporting some of the load of the airplane as lift is still in action. Okay, and we can say that each one of these struts then is going to have a third of the 550,000 pounds that we had originally. Okay, and so another unit that people might use is kips. I'm not always very careful about making the sign right, but at least with bars. But I am we have to be very, very careful throughout the course that we get the sign right. I once had a wish that I would just be able to know whether something is positive or negative. Okay, I still have that wish. I still get confused what's positive, what's negative, what's in or out, right? But this is going to be having an internal force, okay, of about 816 kilonewtons. And you remember internal forces, right? You take a slice, method of sections, method of slices, right? And you can figure out what the internal force is. Okay, how are we doing on time? I'm not doing very well on time, actually. Okay, so, yes, an important question. So how many elephants will you be able to stick on one of these? How much does an elephant, what's like Jumbo the elephant? What's its weight? Or an elephant, a full-grown elephant. I'm going to be thinking in terms of pounds, okay? Bananas? What does an elephant weigh?
4,000 pounds.
Huh?
4,000 pounds.
That's not a bad estimate. That's the right order of magnitude, okay? For now, I'm going to say 10,000, okay? So 5 tons, okay? So a 5-ton elephant, all right, we're talking about 18 elephants on one of those struts. So sometimes it's good just to have a little bit of an idea of just how much load a particular structure might be able to handle, okay? Because this is an airplane that's supposed to be lighter than air, but of course it's not. It's extremely heavy. Okay, Now, this is where we get to the scaling relationships, the scaling laws. If I have a bar that can support 200 kip, right? So what do we say kip is? That's 1,000 pounds. So this is 200,000 pounds. And it has a diameter of 3 inches and a length of 6 inches. Okay. What happens to the amount of load that I can support by this bar based on changes in geometry, changes in dimensions? Okay. So what could we change? We could change the diameter, all right, which would be kind of very similar to changing the cross-sectional area. Okay. Or we could change the length. That's pretty much it if it's a cylinder. Okay, so this is a cylindrical bar. So what do you all think? Before you even come up with the scaling law, if I make the diameter larger of a bar, right, if I make the leg or the strut fatter, okay, it's going to hold more or less. More, right? Okay. Okay, so we have that basic idea. We will cover ad nauseum why it scales the way it does, all right, later. But right now we just want to establish some ideas and some relationships. Okay? And I'm not going to tell you why. I'm just going to tell you that's how it is. Okay? But this one's pretty straightforward, actually, because you can think of a force, right, and then it's being distributed across this whole cross-sectional area, right? And what is a kind of a famous quantity, scalar quantity that we use that has force over some area? Pressure, right? That's pressure. Okay? So you get this idea, I've got force over area, and there's some threshold of force over area before I get to yielding, right? Which is when the material plastically deforms. So we got some idea here, right? So how's it going to scale with cross-sectional area, and how's it going to scale with diameter? So maybe area is easier. If I double the area, does the supportable load, what factor is it going to go up by? Now we're talking about the force. Okay, so how much supportable force? If I double the area. Right, it goes up twice. And like you were getting at, if I said, well, if I'm thinking about pressure, pressure is just pressure. It stays at a constant threshold. Okay? But the amount of force that I can support will go up. So diameter, right, is related to area, okay? And we can say that it's going to scale with the diameter squared, right? Pi r squared, or pi over 4 d squared. Right? And we're going to say it scales with the area. Scales with the area. Okay. And what about length? How does length support the amount that a bar can support? Yes.
Would the load go down if it goes longer?
Okay. Okay. Good. Okay. Good. Joe. Great. Is that what you were going to say back there? Yeah. Okay. So why though, Joe? Or why? Actually, you in the brown shirt. What's your name? Sergio. 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 Okay. Yeah. Sergio. So why? Okay. Yeah. Yeah. So if I make it longer, maybe something like the Romans predicted would happen, which is buckling. Okay, so like and that's really kind of, again, we're not going to get to buckling. We'll get to that in DMC. You're going to hear me say that a lot. Okay, but the length, if it gets to a certain length, and it's kind of this is what's called an elastic instability, right? This column or this bar will bow out and it will whoop, right, and it goes boing, and it's like a cartoon. Okay, but as long as you're below that kind of critical length, okay, for a given load, the length actually doesn't do anything. Okay? So you're right. You have an intuition that if I make something too long, it's going to pop out. If I make a flagpole or something too long and narrow, make something too slender, that's bad. Right? I can't like, but bad. Listen, maybe I should not use that term, but it will fail, okay? Why it fails, though, is not because we've exceeded the strength, okay? It's because we've exceeded the structural properties and it causes it to bow out, not because we've exceeded the material property. So if we ignore buckling, all right, length will not affect how much force a bar can support. Okay, so this is just to give us an idea. Okay, and you'll see in the problems, we're responsible for coming up with ratios. Okay, what is the ratio here? What is the factor? Okay, well, it may be a little bit counterintuitive, but does this make sense? The new force that I can support is equal to the force I had that I could support originally times the ratio of the new cross-sectional area over the old cross-sectional area. Okay? So if the new cross-sectional area is twice of the old cross-sectional area, the A new over AI, or A old, whatever I called it, that will be a factor of 2, right? But if the new area is less, right, than the old area, then it will have a ratio or a fraction that's less than 1. Okay? So this is about just kind of developing an intuition based on simple ratios. The math in this class is simple. Yes, there's a prereq, right? But if you can do, and we will do some integrals, all right, we'll do some derivatives, we will do those things, the math is not going to be your problem. The going from the wording and the problem and the structure and the geometry to the math, that's going to be the problem. Okay? So this is your first opportunity, a ratio. Okay? Now, I'm going to skip some of this, all right, but you can use Colab. There's Colab already available, which is the Python code from the website if you want to do this. So, and you're going to see that in some cases, you can just change the numbers, all right, in the Colab and hit Control-Enter and get the right answer, okay? So you could do that. You could write your own Colab. Why am I mentioning this? Okay, because you haven't done it yet. You have infinite number of tries on all the homeworks, okay? But if you get it wrong, guess what happens? The numbers change. So, and I don't know, I haven't, with Canvas, the way it does its thing, I don't know, how to like not have those numbers change, right? So, if you got a Desmos or if you've got a Colab, all right, that's all set, right, with your equation, and the numbers change, all you gotta do is change the numbers and then whoop, it does all the calculation again, right? So, there are times in this class where we will not work with letters. We won't do algebra all the way, right? But in many cases, it's very helpful to think algebraically and then plug the numbers in, all right? And you'll find the balance there. But that's another reason to use Python. Okay?
Excuse me?
Yes.
Can we use mathematics?
Sure, you can do that. Yeah, do whatever you want.
Are we submitting whatever?
No, you won't be submitting your code, all right? You won't be submitting your code. But Mathematica and Python are very similar, and we have a license for Mathematica. So if you want to do that, you can. What will happen most likely, though, well, it depends. Since we are beloved mechanical and aerospace engineers, the big industry company will say, sure, I give you MATLAB or Mathematica, right? If you are beloved mechanical and aerospace engineer and you go to a startup company, like I did at one point in my life, they're not going to give you that stuff, right? So you gotta, if you want to be resourceful, you're talking, okay, what can I do in Excel, right? That's, or like back then, R still exists. I used R to do run some calculations and stuff. Python wasn't as ubiquitous as it is now. So, but you can do whatever you want. You can use Desmos as well. All right, so again, this is just a little bit. If you want to make plots, you can using Python as well. All right, and these templates are there for you on the website. I'm going to keep going. That clock is way not right. Okay, but we only have 13 minutes left, so I better keep going. All right. All right, so torsion on shafts. Anyone think of places where you use shafts to transmit power? Yes. Yeah, so, yeah, I mean, you got to do something to get from the blades, right, to some type of generator, some type of electromagnetic system, right? Or not, or just thrust, whatever hovers, or if you got combustion occurring, right? But yeah, exactly. A turbine is an excellent example of having a shaft that's going to be under stress, okay, and under torsion as it's transferring power, right? So here's an example of turbo shaft, and then if you look back at the pictures from the Industrial Revolution, right, when you see these factories and you see all these shafts and wheels and systems that they created. In many cases, they were going directly from a water source to be able to power their looms or the other machines that they were running. So we still have many systems that use belts and shafts, and your cars are full of shafts as well, and belts too. And if anyone uses a drill press, anyone ever manually change the speed on the drill press? Yeah? All right. Go. You go, right? So you'll find belts there as well. Okay? And there are also things called torsion bars. Now, I've never played with it. I'm not a car person, I guess you could say. I mean, I drive a car, okay, but I'm not going to go underneath and adjust my suspension on a truck. I don't have a truck, okay, for example. But anyone mess with their torsion bars on a truck? Maybe? Okay, yes, no. Okay, so you can kind of adjust the suspension a little bit. Anyone think of where they use a torsion bar very commonly? Yes? Yes, you're making a gesture. Okay, so interesting. I'm not sure if they. I wouldn't say steering wheel. There's another part of a car I'm thinking about that uses a torsion bar. So torsion bar essentially is a bar. I should explain. A bar that has two ends with leads sticking out of it. Okay, and you apply forces to those leads that then create a torque that twists the bar. Okay. So any ideas where you might? Yes. Okay, so, well, the differential itself is doing something else, but yes, again, suspensions, yes, they use torsion bars, yes?
Something called an anti-roll bar or a swing bar.
Okay, yeah, okay, so again, huh?
Anti-roll bars, so roll.
Okay, so that's interesting. So anti-roll bars, those are bars, they're meant to actually, to take more of a distributed load on them as you roll, okay? And those are going to be forces that are being applied. Yes. Okay, again, suspension, yes. Okay, so I say do not mention suspension. Where do you see a torsion bar? Yes. Okay, all right, so that's still kind of suspension-y, all right? Okay, no. Now we're going off on a different. No, I'm just gonna say no. Right? Yes. Drivetrain? No. Okay. Screwdriver. No. So yes, a screwdriver is going. Okay. So yes. Yeah. All right. I was saying torsion bars. Yes. Are these shafts under torsion? Yes. You're right about that. I'm asking for a torsion bar though. which has got these two leads. It's essentially got some forces that are being applied to these leads, and it's creating a torque. Okay. Window. Okay. Okay. This is great. Thank you for all the feedback. I'm asking a bad question. All right. So, on your trunk. Okay. So, have you ever thought about why is it so easy to lift your trunk? That's a huge hunk of metal. All right. And if your torsion bar ever pops, you will know how big a hunk of metal it is. I mean, sometimes a lot of cars now, the SUVs and the minivans, they have air pistons, okay, instead. But if you go back to your sedan, all right, I have a 1997 sedan. It's awesome. Yeah, it gets horrible gas mileage, but actually I shouldn't. Well, you can leave it unlocked, and no one will ever take anything from you. Okay. But anyway, you didn't hear me say that. No one take my car, all right? Actually, that car, it's very hard. It's not the ignition's hard to break into. Yeah, the trunk, okay, it has a torsion bar in it that allows you to lift it easily, or like, you just pop it, right, and it goes whoop, right? That's because it's a loaded spring. It's essentially a torsion bar is a rotational spring. Yes?
Is the type of spring that's like in a mouse trap, is that also torsion?
Yeah, there you go. Okay, but that usually has coils. All right, but it is a torsion spring. It's not a torsion bar. Okay, but yeah, I mean they might make some that are just torsion bars, but usually it's coil. Okay, torsion bar is like kind of it's almost like an oxymoron because we just said bars are for forces, right? But now we're saying torsion is on a shaft, and we're also talking about a bar. All right. Anyway, great. So those are some attributes. All right, now. How does the supportable load scale with changes in geometry on a torsion bar, or on a shaft? Any ideas? This one is less intuitive. But once again, if I make the diameter larger, what's going to happen? Yes. Oh, the diameter. The length won't affect much. You're right. The length, not really an issue. Okay? But the diameter will. All right? And we're running out of time. Okay? Because we've had a nice conversation. Okay? So if we look, and we'll cover this in detail. Okay? But the supportable load scales with the diameter cubed. Okay, again, we will cover this. There'll be some fun things we talk about. We even bring in TCNJ, all right, to this class. All right, we have, that's the other, that's one of the colleges, right? Never mind. The College of New Jersey will help you memorize a very important formula. Okay, and we have, or area to the 3 halves. Okay, because, right. That's how we relate diameter to area for a circle. Okay. Okay. Again, it's independent of length, but long lengths could again lead to buckling. Okay. So if anyone's ever taken some elastic thingy and twist it, right? You can see that you can get these things to buckle. All right. The last thing we need to cover. And I'll try to get some additional content up so that you're not struggling as much. Some of you will breeze through it, but I'll try to get some additional content up so you can get through the problems. Okay? Is the beam. Okay? Anyone watch diving? Yeah? 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 Anyone dive? No, okay. But all right, good. Prisha, I'm glad you got into the diving. All right? These are beams, right? There are beams, literally, that we call beams in trusses in your house, okay? In buildings, all right? This is a cantilevered beam being used for atomic force microscopy. So how does the load, all right, scale with a transverse beam? Well, again, what happens if we increase the diameter, if it's a circular beam, or if we increase the cross-sectional area of the beam? Is that going to have an effect? Yeah, you betcha, right? Okay, in terms of this is the load it can support. This is force. We're not talking about deflection, okay? Because obviously, if you make a beam longer, it becomes easier to deflect. All right, it's like anyone taking a branch from a tree, right? The longer the branch, the more slender it is as well, right? It's easier to deflect. But the supportable load, okay, so if you think, I've got a force that I'm applying at the end of the beam, all right, and it's a transverse force, that load will scale with the thickness squared, that's h here, and it scales with the width only. So this is a kind of an interesting attribute. And once again, okay, sorry. What did I? Oh yeah. So not once again. Sorry. Yes, it does scale with 1 over the length. Sorry, I spoke wrong. Sorry about that. Yeah. So if I make a longer branch, right, and I apply a force to it, yeah, most definitely it can break. I'm sorry about that. Okay, so those are the 3 structures that we've covered today. I will upload some other videos and stuff so that you can get through the homework a little more easily because you didn't get time to do it. Some of you. That'll be available by Thursday night, so you should be good. So thank you. If you have any questions, let me know.
PowerPoints are going to be available.
They are.
Okay, and when
Oh, not well.